Hi, good morning and welcome to today's session. Today we are going to see the model-free approaches in reinforcement learning. In the last session, we have discussed model-based approach in reinforcement learning, especially Markov decision process and its solution using dynamic programming. Now we will discuss one of the popular model-free approach, namely Monte-Carlo method. Naturally, the second important method we'll discuss in next session, that is about temporal difference method, that is popular with game development, etc. First of all, we will see the need and significance of this Monte Carlo approach in reinforcement learning. Also, the popular model-free methods, they are actually Monte Carlo method and temporal difference. Then, what is really Monte Carlo method? Then Monte Carlo prediction and Monte Carlo control. This is actually the generalization of policy iteration method in MTP, but there are some difference when we are using this policy iteration method in Monte Carlo. Then we will see some simple examples. The need and significance of Monte Carlo approach. Markov decision process models are more specific and can be solved using DP. It is well informative. It will give all the state transition probability matrices and reward transition probability, etc. So it is very easy to develop more accurate models with the help of MTP. And also dynamic programming approach by Bellman is a great support. With minimum effort, we can solve it step by step and stage by stage. But there are some difficulties when we try to model real-life situations into MTP. Most of the real-time cases need not have complete knowledge about the state action transition probabilities. That is a major hindrance in using MTP in real-life problem. The Monte Carlo method finds approximate solutions through random sampling. So the Monte Carlo method is a statistical or stochastic approach to make use of random numbers and random sampling to develop some insightful results or insightful predictions from given state models. Monte Carlo is good option to simulate model with partial information that we have already seen in term 2 topics, how we can calculate value of pi, how we can model a biased coin, and how can calculate the probability with the of a biased die with the help of this Markov model, etc. They're very interesting topics. There are wide use of Monte Carlo methods in physics and simulations of particles, etc. Then there is a funny question, why the name Monte Carlo? Usually new theorems and new models are known in name of their inventors, but we know Monte Carlo is a place. Why this method is called Monte Carlo? Monte Carlo is named after the memory of Stanislaw Ulam's uncle. He is actually the inventor of this famous approach, who that uncle often borrowed money from his relatives to gamble in a Monte Carlo casino. So he's a gambler, and he lost most of his belongings because of this gambling nature. So Stanislaw developed a systematic approach or a systematic way to predict the result of gamble. Actually, this idea was developed during his time in hospital. While playing with cards, he came with some insightful ideas related to random numbers and its uses in predicting unexpected things. That is the base of the Monte Carlo theoretical expedition. So stages in Monte Carlo learning: Monte Carlo prediction and Monte Carlo control. As in the case of MTP prediction and MT control, we have Monte Carlo prediction and Monte Carlo control, but there are some minor changes. To remember Monte Carlo learning and MTP, in a simple way, you just remember this result. You need not to recollect all the mathematical equations to compare MTP and MS. MTP means Markov decision process and MC means Monte Carlo learning algorithm. See, this is the root state space. In MTP, the root state space value is obtained from next state through which this S is connected by an action. So it is a fat structure. S skews out information from all the nearest states through actions. Here it is A. I just denote this action A. Here it is A dash. It is A double dash. So S got information from state values of all the connected states through its actions. So it is called bootstrapping. But in the case of MC, it is a lean structure. It's a lengthy structure or in-depth structure. Start from the initial node, end with the terminal node. Terminal node is denoted by G square. Then it is connected by a sequence of state actions like that. So this is called a episode. Episode is simply a sample starting from initial state to the terminal state in the form of sequence of states and actions. Okay. One another difference is that it will never take state values to the previous states. See, this is the end state. This Monte Carlo method never take state values to the previous states. So this is the first state. This first state never connect to second state in terms of state values. It is connected to different states just by actions. Okay, one is a fat structure, another one is a depth structure. The Monte Carlo method requires only sample sequence of states, actions and rewards as in this table. This second figure shows the Monte Carlo. It starts from the initial state and moves through some states, then reach the end state. It contains all these, but in our MTP it only takes one step transition, S to S dash, that's all. It will never take information from S double dash, suppose in the next level directly. It always moves in one step transition. Then how we can predict Monte Carlo? It's very simple. First we initialize a random value to our state values. You just give random values to all these state values. Initially we put 0 to all state values. Then we initialize an empty list called the return to store our returns corresponding to each state S1, S2, etc. We just put a list here. Then start an episode, and for each state in the episode we calculate the return using gt is equal to sigma k is equal to t minus 1 gamma raised to k r k plus t plus 1. This is the direct formula to calculate a return using the immediate rewards. This gamma is the discount factor. If gamma is equal to 1, it is simply arithmetical sum. That's all. That means we start an episode, and for each state in the episode we calculate this return. Next we append the return to our return list. For each state we have this return. We put it in the list. Suppose we do this in 100 episodes corresponding to each state. That list contains 100 elements, 100 values. That is the return corresponding to different episodes. Now last step, finally we take the average of return as the state value. See, the state value is simply average of return for every state. For this state I calculate return in different episode and take its average. For this state I just calculate average of all returns, not the state values. It will never take state values from the state S1 to S0. It will not possible. In this Monte Carlo approach, we never make use of the state values. We use the rewards, average rewards. Then run this over infinite episodes. We have to get information by running over various episodes. It is similar to learn a game. We just start a game and play somehow to the end of the game. That is one episode. Then we know, as an agent, we know the importance of various states, and we know the reward corresponding to different state. Mathematically, we can call it as reward. Then I try the game once again from the start to the end. That is second episode. If I do it 100 times, I play the game 100 times. That is 100 episodes. During this course of play, I just mark the reward for each state. Actually, it's a return for each state using our return formula GT. Then I mathematically take the average, simple average or empirical expectation. The empirical expectation or simple average is the state value corresponding to each state. That is the idea. Then now just compare MTP and MC within 5 points. Monte Carlo methods do not bootstrap. I already explained. It will never take the values of nearest state. It just take the average of its returns. MC method run only a randomly samples episode, but the DP sweeps over all episodes in state space. As we see, it is in breadth form. This Monte Carlo just move on samples of states and actions, but MDP is not like that. It takes all the values of state, all the state values near to a particular state through its action. So it is more depending on the nearest state, but the MC or Monte Carlo is independent of state values. MC is a model free while MTP is model based. MC is make use of just average return. It will never rely upon any probabilities, but MTP is fully based on the transition state probabilities and reward probabilities, and so it is model based. MC is not based on any model. It is model free. It is based on sample averages. In MC, the computational expense of estimating the value of a single state is independent of the number of states, because it never make use of the state value to calculate the state value of another state. So it is independent of the number of states. And in MC calculate state values on episodes. That episodes never contains all the states. One can generate many sample episodes starting from the state of interest. We can start episodes from a particular state, averaging returns from only these states, ignoring all others. This is the third but very important information to make use of this Monte Carlo methods in development of games. That is another thing. We can start an episode from any state. It doesn't matter. But in the case of MTP, Markov decision process, we have to start from the root state and we sweep over all other states to the end state. That is the main difference. Then types of MC prediction. Then prediction means we start with a policy and we try to evaluate how good that policy to our agent. That means we evaluate the policy. That's all. MC method uses sampling method on state value estimates episodically. So number of occurrence of a state in an episode do matters. That means it is moves over the different states occurred in that episode. If a particular state repeat many times, automatically its state value contribute much to the value of the game. Okay, there are two types of predictions. One is first visit prediction. That means suppose this is a state that occur in a particular episode. Its value is calculated as average of all its returns. But in first visit prediction, the average of the returns following first visit to S. We consider the first visit to S only for taking average. Every visit prediction is not like that. It will count each visit of that state to calculate the average. These ideas are important while we are discussing this Monte Carlo. It is similar to this snake and ladder game. Suppose I am playing snake and ladder game, then I just cover the state 10 position 10, then at the next position I got a ladder, then I go to 50, then I just toss the die, I got 1, that is in the snake cell. I got snake bit and come back to the cell 3. See, I already covered 3, but due to this snake bit I come back to 3 again. This is my second visit. In this case, I am not consider that visit for calculating the return, and so the second visit will be discarded from calculating the average, because I have already covered that state in the initial state. But in the every visit prediction, it is not like that. I count the return of a state as many times as it occurred in a particular episode. Okay. Now we just look into the pseudo code for the first visit MC prediction. We got every visit MC prediction from the same pseudo code by changing a single line. Consider the policy pi is to be evaluated. I initialize v of s is equal to 0 for, it is not necessary to 0, we can put any arbitrary value, doesn't matter, for all s in this given state space. Then I create an empty list, return s. Then loop over all episodes. We have to consider all possible episodes in order to get a better approximate value to each state. Then generate an episode following pi. Using this policy, I generate an episode s0 to a terminal state with action a0 reward r1 action state s, then it leads to a state s1. Then I take the action a1, I got a reward r2, move to state s2, etc. Then as usual I start with g is equal to 0, initial return is equal to 0. Then loop for each step in the episode. This is my episode. I start with the end state as in the case of MTP. So t is equal to t minus 1, t minus 2, etc. 0. Then return g is equal to gamma into g, where gamma is the discount factor, plus rt plus 1. Rt plus 1 is the return or immediate return or reward. Now when we put t is equal to t minus 1, what do we get? rt minus 1 plus 1, that is rt, that means end return. So gamma into g plus end return is my present return at state st minus 1. Now you just look into the first visit. If this st appears in this sequence of states, remember I am in state t, so that state t means st. St come here to the rightmost. Now read this. I am at the position st. If that st is not appear in this list, in this sequence, that means this st is in the first occurrence. I repeat, I am at the position t. So st, this is the sequence of states s0, s1, etc. st minus 1. So st will come naturally to the next, to the rightmost side. So my st is here. I am standing here. Then I look here. This st appears in the list. That means st occur even before this occurrence. That means it is the second occurrence. Unless it is not like that, that means st not appears in this list, or in another words, st is the first occurrence. See, st is not appear in this list means st is the first occurrence. So that is why it is called first visit. If it is a first occurrence, include this g into that list. Corresponding to the state st, I create an empty list. In Python, you just think as an array. In that array, the first column, there is a first column. That first cell, I just add g to that cell. So I got the first return. Then v of st is equal to average of return of st. Then v of st corresponding to that st, this return is average of this st. I do this over all episode. So if I do it in 1000 episode, I got 1000 values corresponding to each state. Then when I take the average, this average of individual returns of states. If you delete this line, unless st appears in s0, s1, etc. st minus 1, this first visit condition will be eliminated. That means this algorithm automatically converted to every visit MC prediction. See, just delete this particular line. Then Monte Carlo estimation of action values. It is a very important point. Actually, in MTP, we calculate the state values using state action values because the model is well known. We do have all the information about the model. But here we calculate the state values directly as average return. But it is important to note that when I make an action from a state, it will definitely affect my return. For example, in the same snake and ladder example, I am in the state 10, then in the next cell there is a snake. If I toss the doors and I got 1, then what happened? I just entered to the snake cell and I got bit and come back to a very lower level or lower state, isn't it? It is just because of that return 1. That action is 1. That one cell, I just moved one cell to the right. If I got 2 while tossing that particular die, what I mean, I just escape from the snake. So if I got 6, I may get a ladder to the end of the game, isn't it? So in this Monte Carlo approach, the action is more important than state. Action is important, but these action values are approximated using the average values of returns of corresponding state. So it is not that much a good value, good measure. It is not a good measure to assess the policy. Okay, so it is better to calculate the state action values. Then how we can calculate state action values? It's very simple and it is straightforward. There is no way out. We have only our return, state-wise return. Now we incorporate action 2. That means I just consider each state action pair. Estimate Q pi of the state action pair, the expected return when starting in state S, taking action A, and thereafter following the policy pi. That means I just stand on the state S, then look around. What are the actions? Suppose there are actions A1, A2, A3, A4. Then just pick A1. I am going to find out Q pi of SA1. Then find out the return corresponding to A, just looking to the terminal state. As in the previous example, we calculate GT corresponding to A from the state A, from the state S with the action A. We will do this calculation to all actions in that state. Q pi SA1, Q pi SA2, etc. Q pi SA5. Suppose there are 5 actions. This is for the state S. I do this for all state action pairs in the model. So what you get? For each action, there is a list. If I did it 100 times, that particular list contains 100 values. Then find out average of these 100 values. That is the state action value. See, there is no other tool to calculate action value and state value. Simple average. We may make use of simple average of return, whether it is state value or whether it is state action value. Then every visit MC method estimate the value of the state action pair as the average of the returns that have followed all the visit to it, as we already explained. In the first visit case, we take average in the first visit. Every visit, we include that particular action in every visit into the state and following that particular action. Then Monte Carlo control. So we explained what is Monte Carlo prediction. Then in the case of Monte Carlo prediction, we have to calculate Monte Carlo Q values and also state action values. The state values and state action values. We have devised methods, that is simple average of returns. Now we move on to Monte Carlo control. Monte Carlo control means we are evaluating that particular policy, then we have to make it better by some better approximation. How we can make better approximation? By improving the policy. So as in MTP, we will use a generalized policy iteration. It has two steps. First one is policy evaluation uses state action values. Second one is policy improvement. See, this is a key point. In MTP, we use state values for evaluation. In MC, we use state action values. That is very important difference between MTP and MC. The next step is policy improvement. We repeatedly do it. We got a better policy, and so we got optimum policy and optimum state value to the given model. So this is our GPI, generalized policy iteration structure. I start with an initial policy pi. Then using this pi, I calculate an approximate value of q pi. Using this q pi, that is q values, I just identify the q or the action which has the maximum return. If that particular action is not included in this particular policy pi, I just add that action into this policy. So the policy will change. That is a policy improvement. Now we just evaluate that policy using this q value. We repeat this iteratively. After a certain state, we don't get a new action at any state which has a maximum, which has a state value higher than the existing actions in the given policy. That means the further improvement is not possible. In such situation, we can say that this model is converges to an approximate optimal solution. We cannot say that it is an optimal solution, because the quality of that optimality is depending on the number of episodes that we are considered in our q value calculation and state value calculations. Suppose we take 2 lakhs iterations or 2 lakhs episodes, that approximation may be very much near to the optimal value. If you take only 10 episodes, then that approximation is not that much good. That is the idea. That is why we use this type of arrow to show approximation. An evaluation improvement strategy. As in the case of MTP, we will show this an evaluation improvement structure. So this is a competitive and cooperative schema. Initially we start with a policy pi naught. Then using this pi naught, I evaluate q pi naught, not v pi naught. In the case of MTP or Markov decision process, this is not q pi naught, v pi naught. Now I calculate u pi naught. Then I make some improvement in the policy by adding some q which has a q value, some actions which possess higher q value. Then improvement happened. Then evaluate it. So I got q pi 1, a new evaluation. Then I improve it, and finally further improvement is not possible. That means the improvement in q values are not that much significant. In that state, we can say that the policy converges to an approximate policy pi star, and the corresponding evaluation, q evaluation, is the q value corresponding to the given model. Okay, that's all. But the main difference is that we are using q values, and even the q values are created with the help of averaging return. So you have to make sure that it works well, and that is why the convergence is very important. To make the convergence always, we have to take more episodes while calculating the q values and also the state values. Okay. Now there are various types of Monte-Carlo control. This is the generalized policy iteration, but these policy iterations may happen in a different way. The control structure of the Monte-Carlo may different variations. There are two types of Monte-Carlo control. The first one is MC control with exploring start. A second one is MC control without exploring start, and that without exploring start is divided into two classes. One is on policy method and second one is off policy method. That means nothing. This without exploring start will attain with the help of on policy method and off policy method. So first of all, we will see what is MC control with exploring start. Exploring means we are going to visit more states and more actions. How we can attain this? One approach is randomly select state and actions. We allow the algorithm to select actions and state randomly and allow it more times. So automatically it scan through the state space randomly and it collect more states and more actions. Okay, that is the exploring idea. Then we choose the actions with the maximum Q value as for the improving action. Add this into the existing policy, and so the policy will be improved. That is one idea. Look into that. This is the Monte-Carlo control with exploring start. Then I start initial state pi of s element of AS arbitrarily for all s element of s. We calculate pi of s. Pi of s means policy value. Then Q of SA, the action value element of R is a real number for all s element of s and a element of a element of A of s. That means action space. That means initialization. Then returns SA. Return corresponding to this action A at the state S is equal to an empty list. Initially we create empty list for each action. This is for each action at each state. Then loop of forever for each episode. We are going to repeat some operations on all possible episodes. Choose S0 element of S and A0 element of A of S0 randomly. See, that is the idea. We randomly select state and action such that all pairs have probability greater than 0. That means all these actions and states can be taken into the consideration. Positive probability means there is a chance, there is a positive chance to choose all these actions and state. That ensure exploration. Generate an episode from S0, A0 following pi, S0, A0, R1, etc. to RT as in the previous case. But remember, this S0 need not be the start state. It may be any state. We can start from any state. Then we initialize the return G. Then loop for each step in this episode. There are many states S0, S1, etc. ST minus 1. Then from the end we calculate return G. Then this is the first visit algorithm. That is why unless the pair ST-AT is a pair, the state ST and action AT at ST does not appear in the list. That means this is a first visit. Append G to return of ST-AT. We add or the real meaning is just add this return into in a particular cell associated with this action AT at ST. Then Q of ST is the average of returns of ST-AT. We calculate the state action value as average of these returns. Then pi of ST is equal to R max A Q of ST-A. That means we just calculate the state action value for all actions in that particular state ST. Then choose those action A. See arg max A. That means I choose an action A which has maximum Q value. I repeat, choose the action A which has maximum Q value. I assign it to the policy. That means policy is changed. Remember, this policy change happened this episode. So in the next episode we are using this new policy. That is why it is called online control, online policy updation, because in every episode this policy is upgraded and we use the upgraded policy to the next episode. Okay. Then MC control without exploring start. That means we have to control the exploring. That means we are not allow this algorithm to start at any state and action. We fix at this particular algorithm will start in that particular state and action. Okay. Then some type of exploration is necessary. For that we use some simple trick that we have adopted in Bendick models. So computational complexity of MCC with exploring start increase with number of state action pairs. That means if more state action pairs are in the model, then automatically computational complexity increases. this game, if it is incorporated in a game, that game will be slow or game will be hang because of this computational time. In order to calculate Q value and state value, it will take much time because the model contains more state and actions. That is the reason. A better solution is to introduce revised strategies in policy improvement. See, in policy improvement, there are two approaches. One is on policy with the epsilon soft policy. The soft policy is actually generalization of epsilon greedy policy. Then off policy with important sampling. See how the policy improvement will adjust it. In the on policy case, I am using epsilon soft policy. In the off policy case, I am using another trick that is called important sampling. That means I am averaging based on some weighting. I average these Q values based on some weighting. In the on policy case, I select the policies based on epsilon soft policy. That is the two key ideas that we are using in MC control without exploring start. It's very easy to understand this on policy MC control with this pseudocode. The algorithm start with the parameter epsilon greater than 0 because I am going to use epsilon soft control. Then initialize pi, an arbitrary policy. It's a soft policy because it ensures that all states and actions will be considered for selection. Then Q of SA is element of R for all S element of S, A element of A of S. That means assigns initialize these values to Q of SA. Then return S comma A, that is an empty list to store the return corresponding to each action in each state. Then repeat for all episodes. Generate an episode pi starting from S0 to ST minus 1. That means this is a strict policy, a strict episode starting from S0. We cannot start from any arbitrary state. Then loop for each step of episode. T is equal to T minus 1, T minus 2, etc. up to 0. That means we calculate this return from the end node. That's all. Unless the pair STAT appears in this list, that means it's a first visit approach. If we remove this particular line, it changes to every visit MC control. Then append G2 returns STAT. Then Q of STAT is equal to average returns of STAT as in the previous case. Now this is a key change. A star is equal to argmax A of Q of STA. That means I am just go to the state ST, then look over all actions and just mark the state values of each action in a list. Then identify the maximum value. Then choose the action with the maximum value. That is A star. That means A star corresponds to the action which have maximum Q value at the state ST. We will do this at every state for all A element of that state ST. That means now we compare every action with this A star. If that A, arbitrarily chosen action A, is A star, that means it is the maximum valued action. Then assign a probability to choose that A from the state ST as 1 minus epsilon plus epsilon by cardinality of A of ST. This is a real value. That means if A is A star, that means A is the maximum valued action at the state ST, then this is the probability that that action is chosen from ST to the policy pi. If that A is not the maximal action, then the corresponding probability is epsilon by cardinality of A of ST. So it makes that every action should have a positive probability. But remember, it gives higher probability for maximum valued action. So if A is the maximum valued action, definitely it will be chosen for this new policy. If it is not a maximal action, but there is a chance to choose that particular A to the next policy, but the chance is low. That depends on this epsilon. If we choose higher epsilon, automatically this one, the non-maximal action will be chosen to the new policy. So we can adjust or we can control the selection of action to new policy. The policy improvement can be controlled with the help of this epsilon. That is why it is called on policy. Again, we do this upgradation or updation of this policy within this loop. Repeat for our each episode. This episode it will happen. So this new policy will be chosen for the next stage. That is why it is called an on policy. Next is off policy. In order to understand the off policy, just look into the auxiliary tool that is called importance sampling. Then what is importance sampling? As its name suggests, it gives the measure of importance of a sample. Importance sampling is a general technique for estimating expected values under one distribution given samples from another distribution. That means this method helps us to estimate expectations by selecting samples from one distribution. Then using these samples, I will get expectation of the same samples under another distribution. That is a trick. We take samples from one distribution, but this importance sampling approach will help us to convert the expectation into another distribution. That is a probabilistic approach. We use the conditional probability to facilitate it. We can make it in the Bayes theorem or Bayes classifiers. We are using the same thing. So we use with the help of conditional probability, we get the conditional expectation from the given samples under one distribution. I create conditional expectation based on another distribution. This is a very most helpful idea in order to use it in offline mode in MC control. Then what is the practical side of this importance sampling in our off policy MC control? We apply importance sampling to off policy learning by weighing returns according to the relative probability of their trajectories occurring under the target and behavior policies. And this is called the importance sampling ratio. That ratio is weighting. Weighing parameter is called the importance sampling ratio. See, there are two new terms, namely behavioral policy and target policy. It's a very simple idea. Target policy means that is a real greedy policy that explain the model, that explain the full functioning of the model. That is the real policy behind the model. But we don't have the full information about the model initially, so we start with the behavioral policy. That is based on our knowledge, our trial and error approach. Then what we are going to say, the behavior, we are going to convert the behavioral policy into target policy. How we can achieve this? By reducing the difference between these behavioral and target policies. That is a key idea. We just minimize the error between these two policies. And finally, our original policy, that is a target policy, will same as our behavioral policy, or the behavioral policy is converted to the targeted policy. They will become same. So this is the off policy Monte Carlo control. As in the case of on policy, we start with initialization. Then a Q of Si is element of R is a real number. We can choose arbitrarily random values, or it's very easy to put it 0. Then C of Si is as 0. C of Si means cumulative weight. We are going to apply some weighted sum. So weighted sum can be stored in a variable, that is C of Sa. The cumulative sum at state S for action A is 0. Then pi of S is equal to argmax A Q of Sa. That means I am creating our target policy. For this Q of Sa, arbitrary values, I am choosing those actions with the maximum return, and it form the target policy. This is my target policy. Now I am going to create behavior policy, then upgrade it into target policy with the help of my importance sampling method. Importance sampling method is a tricky approach to convert the samples from our behavioral policy, and it calculates the expectation. That expectation will be will be intact with our target policy. See that difference? I am taking samples according to my behavioral policy, but with the help of importance sampling ratio, I convert the expectation under the behavior policy into expectation under target policy. Expectation means average. So I need average with respect to the original policy. I got it with the help of this importance sampling ratio. But we do it not analytically, that means in a full-fledged formula. We do it iteratively. So loop over all episode. Then B is any soft policy. You just start any policy. That means you should give positive probability to each state and action. That means every action and state has the possibility to chosen under the given policy. That is very important. Then generate an episode using B, that is behavioral policy, S0 to ST-1. Then G is equal to 0. Initial weight is equal to 1. There is no weightage initially, so full weight. Then loop for each step of episode. T is equal to T-1, T-2, etc. 0. That means we start from the end node, end state, then come back to the initial state, and as in the case of MTP, no difference at all. Then G is equal to discount rate into G plus RT plus 1. See, T is equal to capital T-1. When I put capital T-1 here, it is become RT, this RT. So this G is the return for this state ST. Then C of STAT, the cumulative weight is equal to C of STAT, that is initially 0, plus W. I add this W to this. So weight updation happened. So interesting thing is that is C of STAT is a numerical value that indicates how many times I visit the state ST. That means C of STAT gives the counter. That counter gives the total number of times I visit this state ST. In that case, this W changes to 1. This becomes 1 by number of times I visit it. That is simply average. This is incremental mean operation that we have seen in Bandit model. Okay, so it's again an incremental mean. That incremental mean is a weighted mean. Then how we calculate that weighted mean? That is very important. So pi of ST is argmax A of Q of STA. It implies I assign new policy element, that is an action taken from this Q of STA. What is the condition? This A should have maximum Q value. That means I choose an action A which has maximum Q value at state ST. Now look into the next condition. If AT not equal to pi of ST. See, AT not equal to pi of ST. What did it mean? AT means action happened at this state ST. That not is equal to pi of ST. That means AT, the action at ST, is not the maximal action. If it is not a maximal action, then what is the difference in AT and pi of ST? Pi of ST means pi of ST. Pi is our original policy. So pi of ST is the action in original policy. What is AT? AT is the action under our behavioral policy. That means it's a very simple idea. At state ST, the action under behavioral policy not equal to action under target policy. That means there is not matching. At this particular state ST, original policy does not match with our behavioral policy. Then this AT never connect to a new state. That state will be in our original policy. So we can discard this action. So we move on to next state. We choose next episode. This episode is meaningless because this AT, particular AT under this behavioral policy, is not the state action happened at pi of S. I repeat that this is a tricky comparison. The comparison is that I choose an action which gives maximum value under this behavioral policy. I already choose the action A, which gives the maximum value under the original policy as pi of s. This AT not equal to pi of st means these two policies are not matched at the state st. So we can discard that episode. If it is true, then we update the weight by W into 1 by the B of AT given st. This is actually our epsilon soft measure that we have calculated in the previous slide, B of AT given st. So the weight is updated. Then we go to the next state. We repeat this. Then what happened through this process? Through this process, this operation will do this thing. It sum or it create weighted sum of those actions which are matched with the original policy action. I repeat, it take weighted sum of those action which matched with original policy. So what happened? This weight updates, this Q value updates will be similar to that of the original, our original policy. So the new policy created will automatically convert to an approximate original policy. That is a trick. This step-by-step iteration, make the behavioral policy to an approximate targeted policy. Okay. So the important takeaway of this session, the Monte Carlo approach is a sampling method to predict and control a model with insufficient dynamics. Suppose we don't have the full information about the transition probabilities, etc. It is better to choose MC. MC control are of two types, with exploring start and without exploring start. With exploring start, make use of greedy policy. It will choose always the action values with the maximum value. Then the not exploring start has of two type, or without exploring start is of two type. One is on policy, it make use of epsilon soft control on policy, and off code policy, it make use of weighted importance sampling approach to make a behavioral policy at par with the original policy iteratively. Thank you very much. In the next session we will continue with temporal difference method. This is again the another model free method extensively used in machine learning, more clearly in reinforcement learning. Thank you.